The next topic is forced vibrations. This is the final topic of the course. And the simplest example in which one can sort of examine forced vibrations is, again, a mass spring damper oscillator. So we have mass, spring, damper, and then in addition to all these components, we have an external force, F of t. So we have a free body diagram that looks like this. Normal reaction N, gravity acting downwards mg, and kx cx dot, where x is again measured from the equilibrium position or the rest position of the spring. So given this free body diagram, we have an equation of motion. That's as usual, mx double dot equals minus kx minus cx dot plus f of t, or mx double dot plus kx plus cx dot equals f of t. So that's the big sort of force vibrations equation, the prototypical equation. This is the damped version, damped forced vibration. And when we say force, we really mean f of t is not equal to 0, right? That it is of some function of time. So we are mostly going to analyze in this course the undamped free vibration, undamped force vibration. Because this is the simpler case, so that's going to be mx double dot plus kx equals f of t. So f of t could be any old thing, some function of time. It could be some function of time. It's not a great looking function, but it's some function of time, let's say. But for simplicity, we're going to consider the simplest function of time relevant to vibrations. F of t equals f naught sine omega t, okay, where omega is the frequency of the external force, or external forcing f of t, and f naught is the amplitude of the external force. Okay, omega not equal to omega n in general. So omega can be in general different from omega n, and then in some special cases, omega may be equal to omega n, where omega n is the natural frequency. Okay, so we are considering a sinusoidal forcing. This would be a sinusoidal forcing. And one advantage of considering sinusoidal forcing is that a lot of real life forcing is in fact that periodic. Another reason for considering sinusoidal forcing is that you can represent more complex periodic motions or even non-periodic forces in terms of sinusoidal and cosinusoidal forces by using Fourier series. Okay, so that's the rationale for using sinusoidal forcing. Okay, so let's now examine this equation, mx double dot plus kx equals f naught sine omega t. Okay, what is what's called the forced response? X of t. Okay, a response to this force. In your differential equations class, this would be called a particular solution, whereas the free vibration response would be called something else, the complementary solution or the homogeneous solution. This is called a particular solution for f naught sine omega t. And basically, we can assume that x of t is equal to some a sine omega t. In other words, the system, if you excite it with some force at going back and forth at omega, the frequency omega, the hypothesis is that the system also responds at the same frequency. Okay, which is true for at least linear systems. Okay, so let's plug this in. Let's call this equation 1. Let's call this equation 2. Use 2 and 1. So before we can use 2 and 1, we need to compute x double dot, for which we compute x dot, which is minus a or plus a omega cosine omega t. And x double dot is equal to minus a omega square sine omega t. We plug this into 1, so we have m x double dot plus kx equals f naught sine omega t, or m minus a omega square sine omega t plus kx, x, where x is a sine omega t, equals f naught sine omega t, right? So we can isolate things. So we have a minus m omega square plus k sine omega t on the left hand side. So a comes outside, and then minus m omega square plus k is the next one, and then sine omega t comes out on the other side, equals f naught sine omega t. And sine omega t is not identically equal to 0, so we can cancel that out. So what we have is the amplitude of forced vibration, forced response, is basically equal to a equals f naught, namely the amplitude of the forcing function, divided by k minus m omega square. Okay, so that's the expression. If you have an amplitude of external force f naught, the amplitude of the motion a is going to be f naught divided by k minus m omega square, or you can rewrite that, divide through by k, divide the numerator and denominator by k, so you have k over k minus m omega square divided by k. This is f naught divided by k, divided by 1 minus omega square divided by k over m, which is another way of writing 1 minus omega divided by omega n whole square. Okay, so that's a. So these are two good formulas for the amplitude of the forced response. Either one is good. And these will be given on the equation sheet for you to use potentially. In the next video, we will understand how this equation can be used to get intuition about the response of a system to external forcing at different frequencies.